Okay, well, this is the second demo of the vibe-coded Alex operating system that I started just 6 days ago now. And I know that there were many controversial comments in the Reddit comments to my last post, and I welcome that. Of course, frankly, I wouldn't have believed what I'm about to show you was possible just a week ago. In fact, that's why I started this experiment. I know there's been a lot of doubt that this is entirely created by generative AI, so I'm going to show you some of the code today. And I've also made the GitHub repo public, so you can all go and try it out for yourself if you want to. But just to start, I thought I'd show some of you who asked about the process of using the generative model, Codex in this case, how it actually worked and what the communication style was like. So just to show you some of the genuine impressive insight that the model has and what it can do that you wouldn't necessarily expect it to be able to do, I wanted to show you the process of adding or at least fixing the ELF loading code that I've been building over the last couple of days. So for those of you not familiar, we've got ring 0, which is the kernel, and ring 1, driver land. We've now got ring 3 support in the platform, so all of our userland processes live there, and we do have full multi-processing support, multi-process support now, so we can actually run multiple processes with a very basic round-robin scheduler in the OS. But we can also separately build ELF binaries, and we do have a full ELF implementation now, remarkably, and grab them into our OS and run them dynamically, which is what we've been working on here. Now, there was a slight problem with it. It didn't seem to be building it in the makefile. I think I screwed it up walking back in a previous git stash that I did when something broke. So I got it to re-implement it here. So essentially I said, we're not building our user demo 2 ELF binary, which I'll show you running in just a few minutes. And I also wanted to make a modification. The run elf command should take an arbitrary path rather than a statically coded path. So here you can see all of its thinking, logic it went through. So all of this, it looks at the code, it understands the platform from scratch, it builds its context, as it's called in the generative AI world. And I always love looking at the things that it says. So the way that it plans what it's going to do, it sounds very human, surprisingly human, I would say, as it decides how to implement something. And it spent, 5 or 6 minutes writing code here. All of these changes that it made that you can see in the diff sets to implement the thing that I'd asked for. And here is a really interesting thing. So I said that there was an issue with the linker, and it was having an issue with the way that it was laying out memory for the processes, and it understood that. It actually searched some documentation related to that, and it set up my sections here between text and data, so it actually functioned. And then down the bottom, it gives you this full summary, so you can see everything that it's done and where it's done it. After that, so it worked and it ran, and I'll show you that running in a second. But the binary didn't do anything. It just was a main function that was empty. So I told it to print hello process, and then I realized we didn't have a printf function yet, so I told it to go and make one in libc, the little libc we've made. And I was expecting it just to make a thing that printed a string. Instead, it made something that actually re-implemented all of printf remarkably, and obviously that was in its model weights, or it used the internet for that. But it's a fully functional printf that can do decimals, it can do floating points, and strings, obviously. So it did all of that, and it ran, and it printed what it was supposed to do. Sorry, it didn't quite do that yet. It had a page fault on running, so it didn't work. It didn't load the binary, so I told it that. It had a closer look. It had a look at link.ld again, as you can see here. It actually understands the cause of why it didn't work, right down to the machine code level. It actually ran all of the commands that I would have run in order to debug where the binary was being laid out, and it realized that it had an overlap between 2 memory segments, which it fixed here. And then when I ran it again, it worked. But I told it here that it didn't actually print anything. The printf command was in the binary, but it wasn't printing to the screen. And then it realized that it didn't have a syscall to link the file descriptor for the console shell that we've run, to the process that it started. So it went and wrote that code and appended the process, so a process can inherit the file descriptor that it's created in order to do that. Then we ran it again. It had a page fault in closing, but it did print hello process, as you can see here. And then it realized that it was breaking the stack guard in process, and it made a 2-line modification to fix that, and then it worked. So we're going to now go and see what we've got here. But before we do that, I just wanted to say that I was inspired by one of the posts in the OS Dev Reddit yesterday about BIOS versus UEFI, and I realized, why am I using BIOS? We should be in a modern system, using a UEFI system. As a result, I told the system to go and create an entire UEFI architecture and a loader in order to load our kernel, which it's now done. So this entire UEFI loader here, this is not copied from anywhere. I've actually had a look at some of it. It uses our constructs, it uses our concepts, it uses our little cut down libc. All of this, and you can see this in the GitHub that is open now, all of this was written by the system, and it didn't get it right the first time. We had to go through a lot of stepping through things and figuring out why things weren't working, but it did ultimately end up making a fully functional UEFI bootloader, and also modifying my makefile and telling me how to set up OVMF in order to make it function. So let's go and have a look at that. So here, just like before, we're going to do a make run HDD, and you can see now we're pulling up our UEFI screen. And just to bring the serial console to the foreground for a second, you'll notice here that we've gone from our old disk controller to AHCI support. Yes, it wrote an AHCI driver for me. So we're being super cautious here because there was an issue with it earlier where it's sitting and looking carefully and waiting for the disks to come up. We can probably remove that delay now, but it does take a while to boot in order to get the kernel fully up and running, which is fine. It's just being super cautious. But in a second, you'll see, there we go. We've fallen through and we've got our nice little frame buffer console here now, and we've got to the command line. So first things first, let's have a look at the demo of that dynamic binary. So to do that, we actually have to grab the binary from a web server that I'm running on my main computer here, a little Python script. So we'll go through the process of getting an IP address, and yes, we've got DH client, we've got a UDP stack to work with the DHCP, a network driver, and an interface to the RTL device that's exposed by QEMU. So here we go. We've got our lease. Just to prove that it works, we're going to ping the internet. Fantastic. There we go. Oh, I've just realized that when I press Control-C here, because I haven't intercepted that trap yet, it's going to kill my my OS. So we're actually going to have to restart that now, which is a bit of a pain. But just while we're doing that, if we go back to our code window, just while that's loading again, you'll see all of the code that it's created now, and it is quite substantial. We've got a full widget library, and we'll have a look at that in video mode in a moment with the task manager that we've got. We've got a crypto library, so that supports our TLS integration into wget. We've got our AHCI driver, we've got our keyboard and mouse, which is still PS2. We've got our network driver there, we've got a hardware timer, a video driver, straight old VGA driver that works quite well. And we've got a bunch of commands that we've made that work onto that CLI. So it's really quite dramatic how much of a platform we implement now. So let's go through this process again. There we go. So now we're going to get our binary, the ELF binary from our main OS. That's just in the build folder if you want to replicate this while you try it yourself. So we're just going to grab it from build userdemo2.elf. We'll hit enter there. There we go. So it's grabbed our binary into a file called userdemo2.elf, which we can see just here in the root. Now we're going to do our run elf userdemo2.elf. And just as a reminder, if we go back and have a look at this code, userdemo2, where is it? Userdemo2, here it is here. It literally just prints hello process and returns. So this is using our userland libc and our userland printf, and it's built by the main makefile as a separate binary that we can then pull into the OS via wget, and we can run it. So I'm just going to hit enter here, and there we go, hello process. So if we look at the console, the serial terminal, we can see that it's created a process and its associated thread. It's run the process, and here looks like we've still got an issue with our stat guard violation, so there's a bug to fix there, but it does work and it doesn't crash, which is nice. All right, so let's jump into video mode now. So here is our little video mode. So we're going to start our task manager. So we can see those things running. We've still got a bit of an issue with process cleanup, as you can see here. So they're shown as zombies. Now this is something I had yesterday that I'm quite amazed that it could do it all. This is a fully functional VT102 terminal emulator. So this isn't the same as that text shell before. This is actually fully functional with scrolling support and all of the other things that you might need. So here we're just going to run some of our processes to show that it works. There we go. So we've got loop 1 running, and to show that we can do preemptive multitasking. That's just a loop that sits there with a synchronous timer, so it doesn't have to share, it's not yielding of its own choice, but we make it yield through the kernel interrupt. So I'm going to run loop 2. There we go. So loop 2 is printing A to J, I think. Loop 1 is happily running still there as well, and we can see them sharing just in a round robin fashion between all of the processes that are running. So just as a reminder of what we've seen here, we've got full ELF support, we've got a process model, we've got a task manager, we've got multi-process support, we've got a video mode, it's a UEFI-based system now, so it loads all of the devices, we've got an AHCI driver, we've got a wget implementation and all of the network components behind that. So TCP, of course, a routing table, and all of the interrupts supporting the network device as well. So just incredible. So in fact, if we jump all the way back out now and just kill the OS here, if we have a look at how much code's been written, you can see it's written 37,000 lines of C in the last 6 days. It's just incredible how not just how much is written, but the fact that it works at all, and it works consistently, and it even understands how to fix things when they break.